So, welcome to the lecture that introduces mostly discrete Markov chains. Um, Here's the outline. So, we'll mostly talk about discrete Markov chains as this is generally conceptually easier, and then we'll talk how to get from discrete Markov chains to continuous Markov chains. So, what is a Markov chain? Um, Markov chain is a stochastic process with transition diagrams. And in general, the process is written as x0, x1, x2, where in general xt is a state at time t. And so the very important thing about Markov chains is this famous Markov property that the state at time t plus 1, so xt plus 1, only depends on the state at time xt and not on any previous state. So processes that have this property are called Markov chains. So here's an example. This is the Markov flea example. So flea that is kind of hopping around at random on this diagram and being in different states like sleeping, eating, being bored, etc. So this flea is hopping around in this diagram according to the probability. So if we look state number 1, there's 1 over 5 probability that it will stay at state number 1. There's 1 over 5 probability that it will go to state 5, and there's the 3 over 5 probability, 60% probability that it will go to state 2. So the state space of this Markov model is just the number of the list of labels here. So it's 1, 2, 3, 4, 5, 6, 7. So here is an example of questions we can ask about this Markov diagram, right? So for instance, what is the probability of ever reaching state 7 up here from state 1? Or we could ask, like, starting from state 2, what is the expected time taken to reach state 4? So what's the number of time steps I need, the expected number of time steps I need to reach state 4? Or we could ask, starting from state 2, what is the long run proportion of time spent in state 3? And starting from state 1, what is the probability of being in state 2 at time t? Also, another question is, does the probability converge as t, the number of time steps, goes to infinity? And if so, to what does it actually converge, this probability? Right, so unfortunately, we'll have to start with a couple of definitions. So the Markov chain is this process of x0, x1, x2, and the state of a Markov chain at time t is the value of xt. So for example, if xt equals 6, we say that the process is in state 6 at time t. So the state space, the definition here is that the state space of a Markov chain S is the set of values that each xt can take. So for example, here S in our flea example is 1, 2, 3, 4, 5, 6, 7. And we say that S also has a size n, so the number of elements in the set here, but it can possibly also be infinite. We're not going to cover this, but this is possible. Another definition is that, well, the trajectory of a Markov chain is a particular set of values for our variables x0, x1, x2. For example, in our flea example, if x0 is 1, x1 is 5, and x2 is 6, then the trajectory up to time t equals 2 is 1, 5, 6. And so more generally we refer to the trajectory S0, S1, S2, S3, if we refer to this trajectory, we mean that our variables take the values of the states S0, S1, S2, S3. So essentially, trajectory is just a word meaning a path, describing a path through our a concrete path through our Markov diagram. Okay. So here comes the Markov property, this kind of loss or absence of memory in more formal terms. As I've said before, only the most recent point, or xt, affects what happens next. That is, xt plus 1 only ever depends on xt, but not on the previous states xt minus 1, xt minus 2, etc. So how can we write this more formally? So the probability of being in state S at time xt plus 1 is conditioned on being in state st at time t, at state t minus 1 at time t minus 1, etc., etc. So this is the conditional probability. And since the Markov property must hold, this can just be written that, well, we condition the probability of being in state S at time t plus 1 only on the probability of being in state st at time t. So all the rest doesn't matter. So those two conditional probabilities must be equal for the Markov property to hold. And so this is something we're going to use over and over again, this kind of simplification of this conditional probability. Right, so here's the explanation. So this is the distribution of xt plus 1, and we say that this only depends on xt, and whatever happened before time t doesn't matter for our probability. Okay, so here's the definition. One more definition. So let x0, x1, x2, etc. be a sequence of discrete random variables. Then this sequence of discrete random variables x0, x1, x2 is a Markov chain if it satisfies a Markov property, meaning that those two conditional probabilities are identical, and if this holds for all times t and for all possible states in our state space as 0, as 1, as t, etc. So, for instance, those discrete random variables can be, and we're still in the discrete case, but those can, for instance, be our nucleotides ACGT, right? So those are our discrete random variables, or the values they can take. So one important, notation for the for describing Markov diagrams is a so-called transition matrix. So we can transform those kind of diagrams here with the states and the transition probabilities into a matrix, which is, as I said, just another way of describing the diagram. And what we do here is that we write down the states at time t, like the hot and cold states. Our flea here is feeling hot and cold. And then we put into the rows the transition probabilities to the next state xt plus 1. So if you're in the hot state, remaining in the hot state, the probabilities to remain there is 0.2, whereas going to the cold state, the probability is 0.8. And if we're in the cold state, the probability of going to the hot state is 60%, and the probability of remaining in the cold state is 40%. So this is just like an equivalent way of describing this Markov diagram. Okay, so here we're annotating this by our states, and then each row and each column um, gives us the values of the states or the values this random variable can actually take. And then here, shown in red, those are the actual transition probabilities. More formally, so what we do is that we, along the rows and along the columns, we list all the states. And here in the matrix, then we insert the probabilities, Pij, the transition probabilities from going to state I to state j. An important thing here is that rows actually need to add to 1. I'll explain a little bit later why that has to be the case. So this transition matrix is usually given the symbol P, and it has the state transition, contains the state transition probabilities from going to state I to state j. So in this transition matrix P, the rows represent now the current state, or from xt, and the columns represent the next state, or to xt plus 1. And so matrix entry ij is the conditional probability that the next state equals j, given that the current state is I. Or, you can also state that differently, it contains a probability, the conditional probability of going from state I to state j. So Pij, an entry in this matrix, is the conditional probability of being in state j at time t plus 1 when we were in state I at time t. So the review of probabilities, I already did it for the lecture on MCMC methods, so I'd go through this again. So this is just like a statistical sample. This is not a transition matrix, right? This is just some sort of histogram, if you want so. And well, the joint probability, just to keep that in mind, is the probability of observing both A and B, which is not really relevant in our case. So for instance, the joint probability of having somebody with brown hair color and light eye color is 5/40, which is 0.125. Once again, the marginal probability, just to remember that, is the unconditional probability of an observation A. So for instance, the probability of observing somebody with dark eye color in our sample is the sum of the joint probabilities of observing somebody with dark eye color and brown hair plus the joint probability of observing somebody with dark hair color and blonde hair, and this is 0.5. And so now here's the interesting thing. So the conditional probability, the probability of observing A, given that B has occurred. So the conditional probability of observing A given B is the fraction of cases where we observe B, which, well, B occurs, where A also occurs with a joint probability of AB. So basically the conditional probability of observing A given B is a joint probability of observing A and B divided by the probability of observing B. So for instance, a conditional probability of observing or drawing somebody from our sample with blonde hair and light eye color is a joint probability of having blonde hair and light eye color divided by the probability of observing somebody with light eye color. So this is 0.75. Right. Then again, statistical independence. Two events A and B are independent if their joint probability, so the probability of observing A and B, equals the product of their marginal probabilities. So probability of A multiplied with the probability of B. So for instance, if we look at the joint probability of having light eye color and brown hair, we can immediately see that this is not equal the product of the marginal probabilities of having light eye color and brown hair, meaning that the events are not really independent. So they're basically, if we look at the example, there must be some correlation between hair color and eye color, right? So they're not independent. Okay. So this was just a quick review of conditional probabilities such that we all remember what they are. Right, so we've seen this slide here before. Why I told you something about conditional probabilities is that, well, we're always dealing with conditional probabilities when talking about Markov chains. So once again, the probability as given by our transition matrix here of going to from state I to state j in a time step of 1 is a conditional probability of being in state j at time t plus 1, given that we were in state I at time t. Okay. So here are some notes about the transition matrix. So the transition matrix P must list all possible states in the state space. Then P is a square n times n matrix because xt plus 1 and xt both take values in the same state space of size n. So just by definition of our Markov models. Then the rows of P, each row of the transition matrix must sum to 1. So if we just compute the sum over the rows, over the elements in a row, j, over row I, if I compute the values, the sum over the probabilities, so this is the sum over the conditional probabilities in this row, and finally I get to 1, or this must be 1. And what that actually means, so this is the important thing that you need to remember. So the above equation simply states that, well, xt plus 1, so my next state at time t plus 1, must take one of the listed values, right? It just must take, be in one of the n states of my state space S. Another note is that the columns of P do in general not need to sum to 1 and don't do so. Okay. And well, the other thing I wanted to mention here in terms of notations. So if you're a little bit irritated by this notation here, this is just another way of writing this conditional probability here, right? So the probability of being in state t plus in state j at time t plus 1, given that we're currently in state I. So this is just exactly means exactly the same. It's just a different way of writing it. Okay, so now let us consider t-step transition probabilities, because now we've right now, or until now, we've always been going from t to t plus 1. But what actually happens if I take 2 steps? So let x0, x1, x2 be a Markov chain with a state space of integers going from 1 to n. And just recall that the elements of the transition matrix P are defined as a Pij, conditional probability of being in state j at time 1, given that we were in state I at time 0. And this can just be written in a general form. So for any one-step transition, so this equals, so the conditional probability of being in state j at time 1 when we were in state I at time 0 equals a conditional probability of being in state j at time n plus 1 when we were in state I at time n, right? So this holds for any n, because our Markov diagram essentially does not remains constant over time, over the time steps. Right. And so Pij, again, is the probability of making a transition from state I to state j in a single time step. So we're going from t to t plus 1. So now we're interested in the question, what is the probability of making a transition from state I to state j over 2 steps, right? So what's the probability of being in state j at time 2 if we were in state I at time 0? So how do we go about that? Do you have any ideas about t-step transition probabilities, how we would do that? Well, we will use our Markov property, right? And this tells us that the transitions from state at time 1, so that's state k, to state at time 2j, this is independent of the transition from state I to state k. So basically here we're saying that those are independent. We're multiplying those two probabilities with each other. So this explains the multiplication, right? So because for getting to state j at time 2, must have gone from state I to state k in one time step, and then from state k to state j in another time step. And the reason why we are using this variable k here is because we need to consider all possible paths through our Markov diagram that can take us from state I to state j. So there may be 1 or 2 or 3 or more intermediate states k at time 1 that take us from I to j. Anyway, so we can now go about and simplify this a little bit and just insert the definition. So insert the transition probabilities from our matrix, rearrange that. And so basically what we see here is that if we want to get the transition probability for 2 time steps, not for 1 time step, we just need to take the power, the second power of our transition probability matrix, and this will then give us the transition probability for 2 time steps for going from I to j. So this is pretty neat and simple. And once again, so here, I mentioned that before, but just for it to sink in. So this is the sum of probabilities, so the sum over all possible paths that can take us from I to j in 2 steps. So this is the sum of probabilities, or so we could take this path or another path or another path over all possible paths, well, with one intermediate state k that takes us from I to j. So this is very important, right? So if we say we could either take this path or this path or this path to get somewhere in statistics, if we have this or here as a logical argument, this always means that we're kind of summing probabilities, right? Because there are different ways that an event, in this case here ending in state j at time 2, can have occurred. Okay, and so the 2-step transition probabilities, in fact, for any n, so not only 0 and then 2, are given as follows. The conditional probability of ending up in state j after 2 time steps, given that we started in state I, equals the conditional probability of being in state j after n plus 2 time steps, given conditional on that we started in state I at time n. And so this is just, as I said before, the transition matrix to the second to its second power. So this is very kind of neat and straightforward. Okay, so just to illustrate a little bit how this or comes about in our time steps, like in a very simple example. So this could be our Markov diagram. So this is a state I, and this is state j after 2 time steps. And then we could really have some intermediate steps here, some intermediate states here, which are listed as k, right? So we could have this kind of fanning out and then fanning in our diagram. And so if we want to have the probability of getting from here, to here, then we just must sum over the probabilities of following those 4 different paths. And you may think of this as, we're still in the discrete world, so we don't have branch lengths or any continuous process of evolution. But if you think about the different ways of getting from A at step 0 to nucleotide T at step 2, depending on the evolutionary process, you could have gone through any intermediate state, or like directly to T, or first to G, first to C, first to A, and then to T. So this is what this actually models. And as I said, as I just said, so we're still thinking in discrete steps here. Right, and so, well, here's an easy question for you, or one that you can probably intuitively answer. So now if we consider 2 step transitions, so 2 time steps, well, how about 3 step transitions? How does that work? So what's the probability of being in state J after 3 time steps, given that we're currently in state I? And probably just intuitively you could have figured that out. So this is a transition matrix P taken to the 3rd power. And the general case with T steps for any T and any time N here is that, well, the conditional probability of being in state J at time T, given that we were in state I at time 0, equals the conditional probability of being in state J at time N plus T, given that we were in state I at time N. And this is just the transition power, the transition matrix taken to the power, raised to the power of T. Okay, so now another question we're interested in is the distribution of our random variables xt. So once again, let x0, x1, x2 be a Markov chain with a state space S, just labeled by the natural numbers. Now, basically what happens is that each xt is a random variable, right? So the fact that it is a random variable means that it has a probability distribution. And we can write down the probability distribution of xt as a vector with n elements. So, for example, consider x0 and let p, or p, the Greek letter, be a vector with n elements, denoting the probability distribution of x0. So if we have this probability distribution, so that's our p vector here that has like a probability distribution for all states in our state space. This means that, so this corresponds to the interpretation that, well, what is the probability? And note that this is a non-conditional probability. What's the probability of being in state 1, 2, 3, 4, 5, etc. up to n at time number 0? So basically this means, or what this tells us, is that our Markov process chooses at random in which state, for instance ACGT, it starts with under the following probability, right? So what's the probability to start in state A? Well, this is PA, right? So this is a kind of the first element of our P vector here. And because those are unconditional probabilities, right? So we're not conditioning on any previous time step, because this is like the the very first state. This is why we also call those p vectors prior probabilities, right? So this is a prior probability in being one of the, well, in our example, 4 states. Okay. Now, given this additional information about the initial probability distribution of our random variable x0, we can now start thinking about the probability distribution of being in state j at time 1. So now, this boils down to the product of, well, the probabilities of being in state I at time 0 and then transitioning from state I to state j. And if we fill in the definitions, this then just goes, this is just a sum over the product of the prior probabilities of being in state I and the transition probabilities of going from I to j. We can kind of rewrite that and we end up with the following formula. So this is the transposed vector p. Typically people are not very rigid about writing this transposed sign here. For the sake of this lecture, I think I've always consistently used that. But in any case, so the probability of being in state j at time 1 is just a transposed prior probability vector p multiplied with a transition matrix p for j. So here we're asking what the probability of ending up in state j at x1 is for starting in all possible states n at x0. Okay. So here, once again, this is a visualization of that. Here's our p vector, so those are the initial states, or the probability in being in the initial states at time 0. So here, for instance, this is 0.2 for being in A, 0.3 for being in C, 0.4 for being in G, and 0.1 for being in T. And so we can be in any of those initial states here, and then have the transition probabilities to t at time step 1 here. And what we do is that, well, we multiply those two probabilities, so the probability of being in state A at time 0 with a transition probability, so we kind of, along this path, we multiply, and then we just add up or sum over the different possible starting positions. Right, and so here again, this is to highlight it like how we're modeling in statistics. We have the or here. We can either be in A or C or G or T in the beginning, and then if we're, and then if we, let's say, have taken the decision that we're in A, we need to take this transition here, so we need to be here. This must have happened with 0.2 probability, and then this transition must have happened with a transition probability from A to T here. Okay, and so what's the probability distribution then of x1? This is again the equation I've shown here that we've seen before actually, and this shows that being in state j at time 1 equals the product of the transposed prior probabilities pt with the transition matrix for all j. So the row vector p transpose t multiplied with p is therefore the probability distribution over all possible states for x1, or so more formally, so x0 is distributed according to the the transposed prior probability vector, and x1 is distributed according to the transposed prior probability vector multiplied with the transition matrix. Okay, so here's an exercise for you. What is the distribution of x2 then? What do you think? So this is pretty straightforward. As before, we need to do some maths, right? So what's the probability of being in state J at time 2? This is the probability, well, of being at state 2, of being in J at time 2, given that we were in I at time 0, multiplied with the prior probability that we were in I at time 0. So we can fill in our previous results here. And so this is the transition matrix raised to its second power multiplied with the prior probability. So this is basically the prior probability vector P transposed multiplied with the transition matrix raised to the second power. And in general, the probability distribution of xt, so xt is distributed according to the transposed prior probability matrix. So you can see here that this always only appears once because this is the starting condition, and then the transition matrix taken to its tth power. Okay. Right, so here is a theorem. So let x0, x1, x2, etc. be a Markov chain with an n times n transition matrix P. So if the probability distribution of x0 is given by the 1 times n row vector P transposed, then the probability distribution of xt is given by the 1 times n row vector P transposed pt. I think there is something wrong here because this should be the power p raised to the power of t as before. So this is the correct notation. I'm sorry, this went wrong. So from x0 being distributed by p transposed, it follows that xt is distributed by p transposed multiplied with p raised to the power of t. Okay, now let us consider something different. Let us consider so-called trajectory probabilities. So recall that a trajectory is a sequence of values x0, x1 up to xt. And because of this very nice and neat Markov property, we can find the probability of any trajectory by multiplying together the starting probability and all subsequent single step probabilities, right? So this is this and I've been so enthusiastic about. And so now let us assume that we are given the following prior probability distribution at time 0. So there's 75% chance that we'll start our Markov process in state 1 and 25% chance that we'll start our Markov process in state 3. So here, what is the question is, what is the probability of the following trajectory, so of observing the following states if we run our Markov process 1. So what's the probability of observing 1, 2, 3, 2, 3, 4? So the probability of observing this specific trajectory is the prior probability of being in state 1, right? And so we know from here that this is 75%. Multiply then, well, with the transition probabilities that take us to the desired state. So here we want to go to 2, then we want to go to 3, back to 2, back to 3, and then to 4. So we just have to multiply all those probabilities. So the prior probability, which is 75%, times the respective transition probabilities, and so the probability of observing this trajectory is 1/10. right? And so here I've just highlighted again the trajectory that we want to take via this blue line here. Okay, and so here's now a nice exercise for you. Given this Markov diagram, the first thing is to find the transition matrix P. Then I want you to find the probability of being in state 3 at time 2, given that you were in state 1 at time 0. Then furthermore, you should assume that the process is equally likely to start in any state at time 0, right? So basically being in the prior probability of being in state 1, 2 or 3 is 1 over 3 for all 3 states. I want you to find the probability distribution of x1. And suppose that the process begins in state 1 at time 0, here. Find the probability distribution of x2. Then the last exercise is that suppose that the process is equally likely to start in any state at time 0. Find the probability of obtaining the following trajectory: 3, 2, 1, 1, 3. So here again you would start with the prior probability of being in state 3 or starting in state 3. So this will be 1 over 3, and then you have to figure out the transition probability. So to 2, then to 1, then of staying in 1, and then going back to 3. So you just have to multiply those probabilities. Okay. Now going to some more advanced topics. So now what we're trying to do is to better characterize different types of those Markov diagrams. So as you've seen in the previous slides, there we had several different types of Markov diagrams that somehow intuitively look differently, and now we're trying to mathematically characterize them a little bit better. So the first thing that we're going to talk about is the class structure. So the state space of a Markov chain can be partitioned into a set of so-called non-overlapping communicated classes. So states I and j are in the same communicating class if there's some way of getting from state I to state j, and there's some way of getting back from state j to state I, right? So basically I can freely move around between states, and I don't somehow get stuck in a state because I cannot leave it anymore. What is important here is that it does not need to be possible to get from I to j in a single step, but it must be possible to get from I to j over some number of steps to be able to travel between those two states in both ways. And so we write this that I communicates with j by this double bidirectional arrow here. Okay. So here's a more formal definition. Consider a Markov chain with a state space S and a transition matrix P, and consider two states I and j in S. Then, given that, we say that state I communicates with state j if there exists some t such that the probability of going from I to j after t steps is larger than 0, and there exists some u, so some number of steps such that the probability of going from j back to I after u time steps is also larger than 0. So mathematically it's easy to show that the communicating relation, so this kind of bidirectional arrow here, is an equivalence relation. And so this means that it actually partitions the state space S into non-overlapping equivalence classes. And here's another definition. So states I and j are in the same communicating class if I communicates with j. So if each state is accessible from the other. Um, Another important thing here to note is that every state is a member of exactly one communicating class. Okay, so here's an example or a small exercise. In here, you should find the communicating classes. So if you look at that just intuitively or by eye, we can see that there are two communicating classes, right? Because there's this one arrow that takes us away from this kind of blue subset or the blue class to the red class, and there's no way back from the red class, so from states 4 and 5 to this state set here, 1, 2, 3. So basically here we observe two classes or two sets or two partitions of our Markov diagram. That's 1, 2, 3, because here we can always, like from 1, we can always go to 3 and back, and from 2 we can go to 1 to 3 after 2 steps, then again back to 2, etc. So basically we have this kind of cycle here and this bidirectional relationship here, meaning that all those states can communicate with each other. Then we have the second communicating class, which is a subset of the state space 4 and 5. Okay, so now, given that we've defined and understood what communicating classes are, what are their properties? So a communicating class of states is called a closed class if it is not possible to leave that class. So that is, the communicating class C is closed if the transition probability Pij equals 0 whenever I is in our communicating class C and the state J is not in our communicating class C. So an example here in the transition diagram from the last slide, class 1, 2, 3, so the first partition here, this is not closed because we can go to the other class, but so we can kind of escape to the class 4, 5, but the other class 4, 5 is closed because it's not possible to leave this class anymore. There's no arrow pointing outwards of this class. So so much about communicating classes. And then there's also kind of a special case that can also occur. So state I is said to be absorbing if the set I is a closed class, right? So if this is a class from which I cannot escape anymore, this is an absorbing state. I can just, like, it's a dead end. I cannot move out of this again.